This is Luke Jane from Vertex Tutors, and I am here to go over an AP Calculus BC free response question. Today we'll be looking at 2015 question number 1. It is a Part A question, meaning that we have access to a graphing calculator, and you will need that graphing calculator for a few of the questions. I'll start off just by reading it out. The rate at which rainwater flows into a drain pipe is modeled by the function r, where r of t equals 20 sine t squared over 35 cubic feet per hour. T is measured in hours from 0 to 8. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by d of t equals negative 0.04 t cubed plus 0.4 t squared plus 0.96 t cubic feet per hour from 0 to 8. There are 30 cubic feet of water at the pipe when t equals 0. So, a lot to digest. I think some of the important things that I would highlight or take note of in the question is that r of t, this function here, is into the pipe, whereas d of t, this function here, is out the other end. So we have an in function and an out function. Notably, these are rates. Okay, that's not the amount of water itself, but rather the rate at which water is coming in or out. So when we were asked how many cubic feet of rainwater flow into the pipe during the 8-hour time interval, it's not asking how much water is there, it's asking how much water has gone through. So that doesn't really matter how much goes out, but only instead how much goes in. So we're going to be looking at that r of t equation as we want to find the area under the curve in order to tell us the total amount that has flowed, not just at a certain point of time, but rather this whole range. So I will basically show you this part here, part A. You can see we're looking at the integral of r of t from 0 to 8, which, since you get to use your calculator, you can just plug in nice and easy. You get 76.570. Make sure to keep your units there, cubic feet. You get to round to 3 decimal places, so make sure you do keep those figures there. And again, simply just a plug and chug calculator problem in order to get the right answer. Next one's going to get a little bit more tricky. Is the amount of water in the pipe increasing or decreasing at time t equals 3 hours? Give a reason for your answer. So if we look again at what I was talking about earlier, the in rate and the out rate, we have these two different functions. So if we want to find the net rate here, right, the total amount, seeing if it's going up or down, we need to do the in minus the out. Basically, if the in is higher, that means that we'll be positive. We're having stuff go up. Whereas if the out rate is higher, that means we're losing material. So it'll be negative and we'll be going down. You get a nice equation here with r of t minus d of t, and all you have to do is plug in at t equals 3, since the question is asking at time equals 3 hours. Ultimately, you could do this a few different ways. You could just tell right away that it equals this by using your calculator. You could show each individual value like I did down here, but make sure one important part about these questions is that they say give a reason for your answer. So essentially you have to always justify what you're doing. Say that because the net rate is negative, that means the amount of volume of water in the pipe is decreasing. Something like that. Simple enough. You just need to put words behind your work and not just have raw numbers everywhere. This next part, part C, I'd say is probably the most difficult in the question. So at what time, t, from 0 to 8, is the amount of water in the pipe at a minimum? And justify your answer. So, essentially, like I mentioned before, we have our net rate. But we also have an initial value, because the pipe comes with 30 cubic feet at time equals 0. Initially, there's 30 cubic feet of water in the pipe. So, if we want to find the amount of water in the pipe, we can't just use the rates. We have to take the integral of the rates in order to find that actual amount of water, that volume. So if we look here, I've written out the equation that uses our initial value, our in value, our out value. I actually missed a 0 to t here, but essentially it's 30, the initial, plus the amount from the flow, the amount from the change. So we can graph this in order to find out where it is negative. So in other words, we need to find out where this part right here is switching. Because if you look at the graph, this is r of t minus d of t, not the integral. You can see that it starts off negative, but switches to become positive, meaning from this point 0 to this point 3.272, the amount of water in the pipe is decreasing. Now, it'll peak, the amount coming out will peak down here at 1.75, and it'll get lower and lower until it's basically 0, but essentially wherever the rate is negative, we're decreasing. So what's important about that is that when r of t minus d of t equals 0, we see the switch going from decreasing to increasing, which means we'll be going from a downwards trend on our volume graph to an upwards trend. So where the rates equal 0 is where there is a min or a max. That's something that you'd expect out of, like a parabola or something like that, where that top point, the rate equals 0, the tangent line is 0, and essentially we're going from up to down, or in this case, from down to up. So if we plug that into our calculator trying to find that point, it is 3.272, which the graph alluded to on that other tab. So if we look now at our equation, we can plug in a few values. We can plug in the 0. Also, 0 itself makes this all equal 0. But also 8, which is a bit different, because if you plug that in, you won't see, it won't be a 0 in that graph, but instead it's an endpoint, and 0 is also an endpoint, but we had to check it anyways. But you do have to check your endpoints to see if that's where the graph ends up being a min or a max. So you can see here, out of these values, this one is the lowest, so the 3.272 hours ends up being our minimum amount of water at, this is in cubic feet. This is actually the amount of water. All right, so pretty good so far, and that just leaves us with a part D, which asks the pipe can hold 50 cubic feet of water before overflowing. For t greater than 8, water continues to flow into and out of the pipe at the same rates that we already have. Write but do not solve an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. So this is actually a surprisingly easier question than we just had in C. I'll show you the equation that is the answer, and I'll explain it. So we have 50 equals 30 plus the integral from 0 to w of r of t minus d of t dt. So essentially, this is exactly what we had up here. Right? We used this equation in order to find the volume of water, which was not what part C was asking for, but rather something that we could use when we justify our answer. Again, you always want to put words behind your work. So here, we want to use an equation that will tell us some answer w. So here, we basically are asking, when will we get 50? So we just use our volume equation up here. We say that the integral is now going to 50 instead of what should be 0 to t up here. And essentially, that gets you your answer. So, question number 1, nice and easy. Just mostly using integrals and your understanding of how the zeros work with mins and maxes to basically get your solution. So, I hope Vertex Tutors was able to help out with this question, and I'll see you in the next one.